you very much, Ms. Zubi, for the invitation and for organizing the event. The lectures will be interactive, and we begin with a discussion concerning these three triangles. My question for you is, what do they have in common? What features do they share? Yes?
The vertices are on the grid?
The vertices are on the grid, absolutely. Let's agree on some terminology. You have a square grid. Let's say that the length of each side of each square is 1. So the grid consists of unit squares. And the intersection points of the grid lines are called lattice points or nodes. And all the vertices are on the lattice. Excellent, excellent. This is the first observation. The triangles are not just hanging out there on blank paper, they are on the lattice. Excellent. Further observations. Yes?
Every triangle has 180 degrees.
The sum of the angles in each of the triangles is 180 degrees. Yes, they are all triangles and they satisfy any property that all triangles satisfy. Absolutely, yes. But what do these specific triangles have in common? Yes?
They seem to have all three edges different lengths.
They have, yes, except this is an isosceles
That's
triangle.
right,
Yes?
They seem to all have roughly the same area.
They actually have exactly the same area. What is their area?
1, 2.
Mhm.
Oh, 1.5.
1.5, yes. The third one is the easiest, 1 times 3 divided by 2. Here from a 2 by 2 square, 4 minus a half. This has area 1, this has area 1. Again 0.5. How would you, again 1.5. How would you compute the area of the triangle on the left? You can take this right triangle. It has area 2 times 5, and then minus the area of this, minus the area of this, minus the area of this square. Again, area 1.5. Absolutely, they have exactly the same area, 1.5. What else do they share? If you elaborate more on your first observation that they have their vertices on the lattice, how do they interact with the lattice? Yes?
They are all like 2 apart. The first and the last point of each triangle are 2 apart on the...
Aha! The horizontal distance between the two vertices is always 2. That's true, yes, that's true. That's an observation, yes. But what else about the actual triangles? See, I could have shifted this triangle. We could have rotated it a little bit. Or this one we could have drawn in a tilted way. What else do they share in the way they sit on that lattice? Yes?
One edge is always at the top.
One vertex is always on the top, yes, that's true. Yes, but again, we could have drawn this triangle with this vertex going 3 units down here. Look carefully. The lattice points are the intersection points of the grid lines. How do the triangles interact with the grid lines, with the intersection points of the grid lines? Yes?
They don't pass through any other intersection points.
Aha, absolutely. They have the vertices on the lattice, but their sides contain no further lattice points. Absolutely. On their boundaries, they have no lattice points besides the 3 vertices. Absolutely, that's correct. Very nice, very nice. What else can you notice about the way they interact with the lattice? Built upon this observation, this was a nice... What else do you notice about the triangles and the lattice? Right? If you follow the boundary of each triangle, you never encounter any lattice points.
they all have one lattice point. inside.
Absolutely! They all have exactly one interior lattice point. So they all have one interior lattice point and 3 boundary lattice points. Absolutely. And they all have area exactly 1.5. Very nice, very nice. This is how they interact with the lattice, and this is about their area. Okay, now what do those 3 figures have in common? The ones on the bottom. Yes?
Same amount of lattice points.
Absolutely. Okay, so let's be careful. Yes, the same number of lattice points. Where? On the boundary.
Yes, sorry.
And inside as well, none of them has any lattice points. So they have 0 interior lattice points, and each has 5 boundary lattice points. The 5 boundary lattice points are placed in a different way. Here you have the 5 boundary points are the 5 vertices. Here you have a triangle with 2 extra boundary points. There you have a quadrilateral with 1 extra boundary point on one of the sides. But they all have exactly 5 boundary points, yes?
Will they have the same area?
And they all have the same area. All 6 of these have area 1.5. Now, if you try to draw a polygon on a lattice with area 1.5, it has to follow actually one of those 2 patterns. Either 1 interior and 3 boundary lattice points, or no interior and 5 boundary lattice points. But in any case, keep this example in mind, it will show up. These are 2 ways to have area 1.5. Alright, now the goal of this talk is to analyze the following setting. You have a polygon. It could be complicated, but a polygon with vertices on a lattice. I will always denote the number of interior lattice points, the ones marked in red. B is the number of boundary lattice points. This always includes the vertices, but you can have further boundary points on the sides. And A will be the area. And we ask the following question. Is there a relationship among interior lattice points, boundary lattice points, and the area? Is there a formula that expresses the area in terms of the number of interior and boundary lattice points? If yes, that would be truly remarkable. If you can calculate the area just by looking at interior and boundary lattice points. If you can find such a formula. Okay, and we'll get to the bottom of this question. We'll analyze it completely. Now you can say that if a polygon is large, it should comprise more points. It should contain more points in the interior, more points on the boundary, and therefore if you know how many points it contains, you should be able to tell the area. But it's not clear. It may be that you have a polygon which is stretched out, avoiding points, avoiding boundary points, avoiding interior points, and yet having a large area. Maybe you cannot tell the area just from the knowledge of the number of interior boundary points. So we'll analyze that question today. Now, let's start with some very preliminary observations. Look at those 2 rectangles, a square and the rectangle 1/4. What can you say from this picture? Something very, very trivial, very easy as an observation, and yet it's worth mentioning. Yes?
It has no interior lattice.
No interior, so both of these have I equals 0. And, yes?
4 boundary lattice points.
And, well, this has 4 boundary lattice points, but the one on the bottom has further boundary, has 4 vertices, but then further boundary lattice points. Yes?
I mean, one's area is 4 times the other.
Absolutely, the areas are not, they do not match. Therefore, the number of interior points on itself does not tell you the area. If you know the number of interior points, you cannot tell the area, yes?
So, the first one has 4 boundary points and 1 area, and the other one has 10 boundary points and 4 area, so it's not directly proportional.
Mm-hmm.
Absolutely, if there is a relationship, it would be more complicated, absolutely. So far, we'll get to that, we'll analyze exactly this. So far, the number of interior points on itself does not determine the area. Look at those 2 examples. Both of them have B equals 8. 8 boundary points. But what about these 2 examples? Yes?
One has an interior.
One has an interior point, the other doesn't, but what about their areas?
Not the same.
Not the same. Therefore, the number of boundary points on its own does not determine the area. If you hope to be able to tell the area, you need to know both the number of interior points and the number of boundary points. Only one of these on its own is not enough. So if there is a formula, it would have to involve both of these quantities. Okay, now we are starting to analyze, exactly in the spirit of what you say, how the area, if there is a relation, how the area would depend on the parameters. Now it's difficult because the area has to depend on two parameters, on I and B. And what we do is we fix, for the time being, the value of B. Let's decide B is equal to 4. So now for a moment we consider only polygons with 4 boundary points, and we'll vary the number of interior points. And then we'll see how the area depends on the number of interior points. That will be easy because the dependence is on only one variable. This looks like more doable as a task. Okay, now look at this triangle, for example. It has 4 boundary points, and what can you say? Let's record our data in a table. How many interior points does it have? Yes?
0.
0 and area?
1.
Absolutely, 0 and area 1. Now what we're going to do, for the moment again, we're narrow-minded, only B equals 4 for us. Now we're going to move the top vertex up. We'll keep moving it up. As we move it up, we never create any further boundary points. You always have the 3 on the bottom, and the 4th is the 3rd vertex. And you'll never create any more boundary points. But this will change the number of interior points. As we change the number of interior points, we'll analyze what happens with the area. What if I move it 1 unit up? What happens with the number of interior points and the area?
1, 2, 1.
Absolutely, 1 and 2. Now it's 2 times 2 divided by 2, the area is 2. I move it 1 unit up, this creates a further interior point. What happens with the area?
3.
Becomes 3, absolutely. Move it 1 unit up, the area is always 2 times the height divided by 2, so it's the length of the altitude. 3 and 4, then move it 1 unit up, now you have 4, and the area is 5, and so on. What can you say from this data, from these experiments? Yes?
The area is always 1 more than the number of interior lattice points.
Now, on this example, yes, the area is 1 more than the number of interior lattice points. That would be because we fixed B equals 4. Yes?
For every interior lattice point, the area goes up by a certain amount.
Exactly. An extra interior point increases the area by 1. Adding an extra interior point increases the area by 1. This is the observation. When B is equal to 4, you can try other values of B, you can play more, and you will observe the same phenomenon. When you increase I by 1, the area increases by 1. We haven't proved this statement. It's just experimental data based on these examples. Now, none of this is more important than the other. Now let's fix the value of I. Now we are narrow-minded. For us, I is equal to 0. And we'll consider many examples with I equals 0. Let's look at this triangle. What are the parameters? Now we look at how the area depends on B, on the number of boundary points. Yes?
B equals 3 and area is 0.5.
Absolutely. B is 3, area is 0.5. Now move the vertex 1 unit up, the top vertex. This creates no interior lattice points. As we keep moving it up, we never create any further interior points. But we change the number of boundary points. As we move it 1 unit up, we increase the number of boundary points by 1. What happens to the area? Now that we've moved the vertex 1 unit up. Yes?
Increases by 0.5.
Increases by 0.5. Now you have 4 boundary points, the area is 1. Move it up again, you have 5 boundary points, the area is 1.5. As you move it up, 6 boundary points, the area is 2. 7, 2.5, and so on. The area is always 1 times the height divided by 2, so it's 1/2 the length of the altitude. Okay, so what is your conclusion now? Yes?
May I ask, is the formula B, half of B minus 1 plus A?
Plus I. Absolutely, yes, that's the formula. Absolutely, that will be the formula. Absolutely, yes. We'll get there, we'll get there. I gave some more experimental data to prepare you to come up with the formula. You already figured it out. Yes, so now, an extra boundary point increases the area by 0.5. What is your name?
Philip.
Philip. Yes, so Philip gets the formula. I'll give you some more experimental data so that You can also guess the formula, but yes, an extra boundary point increases the area by 0.5. Now, we fixed B, we fixed I. What else can we fix? Let's now do some more experiments where we fix the area. Let's decide the area is 2. We'll consider many triangles, all of them having area 2. How can you construct many triangles with area 2? Let's decide that the base has length 2. It has these 3 boundary points. And let's decide that the top vertex moves along a line parallel to the base, distance 2 from the base. No matter where this point is, the area will always be 2, the base, times the height, which is 2, divided by 2. The area will always be 2 as we move the point. Now let's see what happens as we move the point. If it's here, you have the 2 boundary points. Move it. No more boundary points on the middle, 1 interior point. Move it again, 2 boundary points. Move it, again, 1 interior point. As we move the point, you always have 3 boundary points here, 1 on the top, and it's only a question of what happens in the middle. Again, 2 boundary, 1 interior, 2 boundary, 1 interior. What is your conclusion from here? Without getting to a formula, just your conclusion that as you move the point, 2 boundary points get replaced by 1 interior point. Yes?
If the number is even, then it produces a interior lattice point. But if it's odd, then it doesn't.
What is the contribution of interior and boundary lattice points towards the area? How much do they count? Yes?
Each lattice point counts as twice.
Absolutely,
as the boundary
absolutely. 2 boundary points are worth 1 interior lattice point. 1 interior point seems to contribute on these examples as much as 2 boundary points do. Excellent. And what we had on the previous slide was that an interior lattice point, the one in red, contributes 1 unit, and the boundary point contributes half a unit to the area. And all of these 3 bullet points are consistent with each other. The second 2 are consistent with the first. Now you can try to make a guess for a formula. You already guessed it correctly. Let me answer it first. Let me ask it as a question incorrectly. Is it true that the area is I plus b over 2? This could be your guess because it has the feature: if you increase I by 1, the quantity increases by 1. If you increase b by 1, the quantity increases by 1/2. Now this is wrong. You can check up there. For example, you have 4 boundary, 1 interior. The formula would predict area 3, but the area is 2. Or here, I is 0, b is equal to 3. This formula would predict 1.5, whereas the formula is 0.5. And that's why Philip figured out that this is really nice. This is really nice because it has the feature of how it increases depending on if you increase I or b by 1. You just have to subtract a 1. That's how you figured it out, yes? That's how A should change if you increase I or b by 1. And you subtract the 1 just to make it correct. Turns out that this formula holds. Absolutely. This formula holds. Now, this is a theorem by Pick from 1899. It states that for a polygon with vertices on a lattice, just like this one, the area is equal to the number of interior lattice points plus the number of boundary points over 2 minus 1. First of all, it's truly remarkable that such a formula exists. That there is a way from just counting interior and boundary points to figure out the area. This is completely surprising. It's absolutely not intuitive at the beginning. Second of all, it's remarkable that the formula is that simple. It cannot be any simpler than that. It has to depend on both I and b. There has to be a 1/2 at the b, so that the contribution of b 1 more increases a only by 1/2, and the contribution of I by 1 increases a by 1. And you have to subtract the minus 1 to make it work on the basic examples. So it's a simple formula. It exists and it's very simple. We'll prove the formula. Now, a small technical point. I've left a little space before polygon. Oh, let's calculate on this example. Let's calculate this area. How many interior points? Yes?
9.
9 interior points. How many boundary?
7.
7, so 7 over 2 minus 1, 11.5. That was easy. Very quick way to calculate the area of this polygon. Now, I've left some space before polygon. Should this be a polygon? We could have a debate. Someone may say, yes, it's a polygon with self-intersections. Or someone may say, no, it's not a polygon. We have to decide if a polygon can have self-intersections. In any case, should we allow that? Should we allow this? Yes?
I mean, you would just have to take the area of both parts.
The area would be the sum of the areas, but how is the formula going to look like on this example? Is it going to be correct as stated over there? Yes?
No, because the point of intersection.
Absolutely, the point of intersection should contribute here, it should contribute there, because if you believe in Pick's formula and if you split those into two polygons, the formula should hold on each of them, but then this point should contribute here and it should contribute there, whereas now it looks like only one boundary point. It looks like this is only one. If you count this as two boundary points, then yes. So let's say that this is not allowed. Self-intersections are not allowed. And also, someone may say this is a polygon with a hole. Let's agree that we don't consider polygons with holes. For that, Pick's formula fails. You have 16 boundary points, no interior, so the area would have to be 8 minus 7, but the area here is 8. So this is also not allowed. A polygon with no self-intersections and no holes, we call it a simple polygon. Just to clarify that for us, we don't include those types. This is a technical problem, don't worry about this, but just we have to be careful what we mean by a polygon. Okay, now, this formula actually matches all of our previous examples. Remember from the first slide, 1 interior point and 3 boundary points. So 1 plus 3 over 2 minus 1, 1.5. This was the area of these triangles on the top. Or no interior points and 5 boundary points. 5 over 2 minus 1, 1.5 again. This was that other area. This formula is consistent with our examples. Now, we're going to prove this formula. We're going to prove it. It's not a straightforward proof. It will take us some time. We have to work on this. Now, let's check the formula on many examples at once, rather than just do a polygon. Maybe on this polygon you can compute the area in some alternative way and see that it's 11.5. Okay, great, you check the formula here. Let's check it on many examples at once. And let's check it on examples that should be easy. Specifically, let's check it on any rectangle. Let's check if Pick's formula holds on a rectangle. I have a rectangle m by n. Let's work it out. It should be very easy because you know the area. What is the area? M times n, absolutely. And now let's see if it matches with the prediction from Pick's formula. Okay, how many lattice points do I have on the horizontal side? How many lattice points do I have right here in the rectangle? Yes?
n plus 1.
M plus 1. N plus 1, yes. If the length were 1, you would have 2. Now you have one more than the length, so you have n plus 1 nodes on this horizontal side. Up there, again, you have n plus 1. Let's look vertically over here, and we shouldn't count the top and the bottom because they are already included. How many do I have on the vertical side, excluding the top and the bottom, yes?
m minus 1.
n minus 1, absolutely, m minus 1, because it's total m plus 1 minus 2. Now, here, we also have to count the interior points, the red points. How many do I have on this horizontal side? Again?
N minus 2 or n
Minus 1.
N minus 1, because from n plus 1, we subtract 2. The first and the last, we get n minus 1. Alright, so we did the counting. Now let's verify if Pick's formula holds. This should be the easiest case to check the formula. Okay, we have to look at this quantity. I plus b over 2 minus 1. This is what Pick's formula is about this quantity. It should match the area. Let's see. What is I? What is the value of I? Now we've done the numerics, yes?
m minus 1 times n minus 1.
Absolutely, m minus 1 times n minus 1, because the red points, they form this grid, which is n by 1 by m minus 1. Absolutely. Plus half the number of boundary points minus 1. How many boundary points are there? Yes, Philip?
2n plus 2m plus 2.
Just put plus 0 because you have minus 2.
So let's do it a little bit more carefully. It's almost correct. Now, 2 times n plus 1 from the top and the bottom, and then 2 times m minus 1 from the two sides, what remains from the two vertical sides. Now, plus 2 minus 2 in the numerator cancel. The 2 cancels with the denominator 2. So the whole fraction is just n plus m. The whole fraction is n plus m. And if you open the brackets here, you have m times n minus m minus n. These cancel with m plus n, and then you further have a plus 1, which cancels with the minus 1 at the end. What do you get? Mn, exactly what you should get. This checks Pick's formula on a rectangle. It holds on any rectangle. Very nice. By the way, we do this for theoretical purposes, for the purpose of proving Pick's formula. If you have a rectangle and you have to calculate the area, you're not going to do it by Pick's formula, you just multiply m times n. We'll need this in order to prove Pick's formula. Okay, what would be the next easiest case that we can check? Yes?
A triangle.
Absolutely, a triangle. Specifically, what triangle?
Right angle.
A right triangle, absolutely. Right triangle with legs on the grid lines. Let's check it for a triangle m by n. That should be easy. This is the next easy case. If I give you a polygon with vertices on a lattice, this is the next easy case that you can, whose area you can quickly calculate. Okay, let's do it now. On the bottom, the length is n. How many lattice points do we have? N plus 1. N plus 1 again. If the length were 1, you would have 2 lattice points. Okay. Vertically, excluding the bottom, but including the top, absolutely, you have m. Now, I need to know the number of boundary lattice points, so we need to know how many we have on the hypotenuse and how many we have inside, in the interior. Now, you can do that. You can calculate in terms of m and n, but it's a little complicated. We'll avoid it. You can imagine the number of boundary points on the hypotenuse depends on m and n in a more, in a subtle way. If m is equal to n, you will have lots of points on this diagonal. You will have a lot of boundary points. If m is 1, doesn't matter what n is, you will have no boundary points there. So sometimes you have many, sometimes you have few. It depends in a subtle way on m and n. For now, let's just call it k. You have k further nodes on the hypotenuse, excluding the two vertices. We call it k. And inside, let's say that you have I nodes. Again, if you really want to, you can calculate I, but it's difficult. We'll avoid it altogether. Now we have to look at the quantity I plus b over 2 minus 1. This is the quantity of Pick's formula. At the end, what should that be equal to?
Mn over
Mn over 2, absolutely. If we are talking some reasonable stuff, it should be Mn over 2. You know the area of a right triangle. Now let's work it out. We decided that we're not going to calculate precisely for now, just keep it as an I. Plus half the number of boundary points minus 1. Now the boundary points, how many boundary points do you have in this notation? Yes?
m plus n plus k plus 1.
Absolutely. So we start k, and then m, and then n plus 1. Now, that's what we have to figure out. Okay. Go to a common denominator, write it as 2i plus k plus m plus n minus 1 over 2. Now, here is the trick. We don't need to calculate I and k independently. It's possible, but it's a little tricky. It's annoying. We don't need that. All we need is the quantity 2i plus k. 2i plus k is what we really care about. And turns out that 2i plus k is easy to calculate. It's much easier to calculate 2i plus k than it is to calculate I and k separately. Because 2i plus k has a meaning. Now look, I is the number of interior lattice points, k is the number of lattice points on the hypotenuse, excluding the two vertices. What is the meaning of 2i plus k? Yes?
Well, any right rectangle.
Absolutely, complete to a rectangle. It's half of a rectangle. If I complete the right triangle to a rectangle, these I nodes show up there, and 2i plus k is exactly the total number of interior points for the rectangle. This is the interpretation of 2i plus k. That's why it's easy to calculate 2i plus k. Yes?
And then over 2 will give us for the triangle, since it's in the fraction.
So we have to be a little careful. So 2i plus k. Okay, let's do it. Let's do it. Now, by the case of a rectangle. By the case of a rectangle, 2i plus k is the number of interior points in the rectangle. This is why you completed it to a rectangle, because 2i plus k has that meaning. The number of interior points in the rectangle. Now, let's write down Pick's formula for a rectangle. We already know. We've proven it already. So this is the number of interior points. What should I put after the plus? If we evoke Pick's formula for the rectangle. First you have interior lattice points in the rectangle. Plus, yes?
Well then, plus the exterior points.
Plus the boundary points, plus half the number of boundary points minus 1. And what is half the number of boundary points? We calculated it on the...
n minus 1.
Absolutely, m plus n is half of the number of boundary points from the previous slide, and then minus 1. The left-hand side is the quantity from Pick's formula for the rectangle, and the right-hand side is the area. Here we are using the case of a rectangle. This was the easiest case. This is the second easiest case. We are using the rectangle for the case of a right triangle. There we go. This computes 2i plus k in terms of m and n. As a bonus, by the way, we get 2i plus k plus m plus n minus 1. We get exactly the numerator. We get exactly what we need. The numerator is m times n, therefore the whole thing is indeed mn divided by 2. This checks Pick's formula for any right triangle with legs on the grid. Absolutely. Absolutely. Now, we're in good shape. At least we know Pick's formula holds for rectangles and right triangles. Now, we have to prove the general theorem. For a polygon with vertices on a lattice, the area is given by this quantity. Strategy of proof. How are we going to prove it for any polygon? Yes?
Divided into triangles.
Divide it into triangles. Excellent. Divide the polygon into triangles. Draw interior diagonals. Not every diagonal is an interior diagonal. I cannot join this vertex with that vertex. But inside, keep drawing diagonals until you triangulate the polygon. Subdivide it into triangles. Okay, you divide it into triangles. A polygon can be very complicated, but you divide it into triangles. What would you do then? Yes?
Well, you can calculate the area of the individual triangle.
Prove Pick's formula for any triangle. Absolutely, prove it for any triangle. So far we have it for right triangles. We have to do some further work to get it on any triangle, but excellent, we prove it for any triangle with vertices on the lattice. If you prove these 2 bullet points, are we done? Or do we have to do some more work? If Pick's formula, if you convince me that it holds for each of these 4 triangles, is it going to hold on the polygon, yes?
Well, yes, because any polygon is made out of small triangles.
Any polygon is made out of small triangles, but if Pick's formula holds here and here, is it going to hold on the big polygon? We have to prove this. We have to use what we call a gluing argument to show that if it holds for each triangle, then it holds for the whole polygon as well. It's not obvious, because look, this point is an interior point for the polygon, but it's a boundary point here and there. This point is a simple boundary point for the polygon, but it's a boundary point for each of those 3 triangles. The points mess up. They change their roles. We really have to do this gluing argument as well. But this is the strategy. Excellent. Mathematicians love this strategy. If you open an advanced book in mathematics, and if you search, let's say open a PDF and you Control F for gluing, you will find somewhere a proof. of this nature. You have to prove something complicated, you divide it into simple pieces, prove it for each simple piece, but then you have to check that whatever you're trying to prove glues on the whole structure. This is the strategy. Excellent. That's how we're going to prove Pick's formula. And now we start. Now, we're starting with the gluing argument. This is the essential argument in the proof. Now, this slide is the heart of the proof. The whole proof. The idea behind the proof is here. What do you see? Well, again, we can have a debate. Maybe you say that you see two polygons, P1 and P2, that make a bigger polygon P. You see a big polygon divided into two polygons. Or maybe you see a big polygon from which you cut out the polygon P1 and you are left with the polygon P2. We'll be looking at both of these perspectives. Both of these will be useful. Either way, that's what you see. Now, you can ask if Pick's formula holds for the big polygon, for one of the smaller ones and the other small one. Now, let's denote by B1 and I1 the number of boundary and interior points in P1, and B2 and I2 are boundary and interior points in P2. We need the number of nodes on this diagonal, excluding the two vertices making the diagonal. And now let's work it out. We have to write down all the quantities. We have to be very careful, very precise. This is the heart of the whole proof, this slide. Alright, let's look at the quantity from Pick's formula. I was B over 2 minus 1. This is all that Pick's formula is about, this quantity. Alright, with this notation, what is I? What is the number of interior points for the big polygon? Yes? Yes?
I1 plus I2 plus K.
Absolutely. I1 plus I2 plus K. All interior points here stay interior for the polygon. All interior here are interior for the polygon. And all these K are also interior points for the polygon. Excellent. Then I need half the number of boundary points minus 1. The boundary points. Let's calculate the boundary points. Yes?
Well, it would be B1 plus B2 minus K and minus 2.
B1 plus B2 minus K minus 2. Almost. Let's be a little more precise, a little more careful. We'll see it's slightly off. Now, how many blue vertices are there? These are the boundary points of P1, but excluding points on this diagonal. Yes?
B1 minus 2.
Excluding also... So
oh yeah, B1 minus K then.
B1 minus K minus 2. Yep. Because I have K points here, the 2 points, the 2 vertices of the diagonal we also exclude. The blue ones are B1 minus K minus 2. We have to be very careful here. Now, how many red points are there? B2 minus K minus 2, exactly the same. But we have not calculated all the boundary points. We are missing the 2 vertices of the diagonal, so plus 2. This is the correct quantity. That's almost what you said before, just you have minus 2K in the numerator. Absolutely. Now let's see what happens. Something very important happens, and this is why Pick's formula works out. This is the key. You have a minus K and another minus K. When you cancel with the denominator, when you divide by 2, altogether the fraction contributes minus K. And this cancels with that K. That's why it doesn't matter how many points you have on the diagonal, and that cancellation makes it all work. So the K cancels. Now look at the 2's. One of the minus 2's cancels with the plus 2. So altogether you have a minus 2 divided by 2 in the denominator. You have a minus 1 coming from the fraction and another minus 1 at the end. So what quantities do you have? You have I1, you have I2. B1 over 2, B2 over 2, they stay. And then 2 minus 1s, yes?
Well, you have P1 and P2.
Absolutely, you have the quantity for P1. I1 plus B1 over 2 minus 1. This is exactly Pick's formula, the quantity from Pick's formula for P1, plus the quantity for P2. Absolutely. And this equation, this equality, is what makes the proof work. By the way, if Pick's formula holds, this better be true, because this has to be the total area, this has to be the area of P1, this has to be the area of P2. We prove this equality, and now we just get the rewards. If Pick holds for P1 and P2, if the formula holds here and it holds there, what can you say? What can you say about the first bracket? If the formula holds for P1, what is the value of the first bracket? It's exactly the area A1. If Pick holds for P2, the second bracket is exactly the area of P2. That's what Pick's formula means, that these quantities are equal to the areas. So if Pick holds for P1 and P2, look at the quantity for the big polygon, I plus b over 2 minus 1. That quantity is the sum of the two brackets. But the two brackets are the two areas, therefore it's equal to A1 plus A2. And A1 plus A2 undoubtedly is equal to the total area. And therefore the quantity from Pick's formula for the big polygon is equal to the area. And this proves Pick's formula for P, therefore you can glue. You can glue polygons which satisfy Pick's formula, and at the end you do get a polygon which also satisfies Pick's formula. But you see, this was not automatic. We had to do some work. We had to see this cancellation of the K. We had to do some work, but now we have the gluing argument. This is again the heart of the proof. Now that we're here, it's convenient also to give the alternative, the cutting argument, the second viewpoint. If you look at this not as P1 and P2 making P, but P2 made out from P with P1 removed. Now, let's suppose that Pick's formula holds for P1 and the big polygon. Holds for P1, the big one, and P1. What does that mean? What does that mean about the three quantities here in this equality? What does it mean that Pick's formula holds for P1? It means that the first bracket is exactly the area of P1. And if Pick's formula holds for the big polygon, this quantity is exactly the area of the big one. So it means that these two quantities are the corresponding areas, if Pick's formula holds for the big one and for P1. And therefore, what can you say about this quantity, the quantity for P2? Yes?
A minus A1.
Absolutely! This quantity is this, the left-hand side minus the first bracket, but now it is A minus A1. And what is A minus A1?
A2.
Absolutely, A2. And therefore, P2, look at it, it satisfies Pick's formula. It satisfies Pick's formula, therefore Pick holds for P2. You can cut. From a polygon that satisfies a Pick's formula, you can cut out another polygon which satisfies Pick's formula. You're left with something that also satisfies Pick's formula. You can glue and cut. Now we are ready to give the proof. Look at... Now, what was our strategy? We had to prove it on an arbitrary triangle. How do you prove Pick's formula now on this triangle, on an arbitrary triangle? Yes?
Maybe make it into a rectangle.
Absolutely! Draw a rectangle, put it in a rectangle, and then divide and then subtract three small right triangles. Absolutely. Now, you may try to drop an altitude and split it into two right triangles. The problem with this is that if you drop a perpendicular, you may not hit a lattice point. Pick's formula demands that your polygon has vertices on the lattice. So you don't want to drop a perpendicular. But naively, if I ask you to calculate this area, if I give you this paper and you have to calculate the area, what you do is you put it in a rectangle. Now, we know Pick's formula on a rectangle, it holds. We know it holds on any right triangle. So we can cut out the three right triangles, and therefore Pick's formula will hold also on your initial triangle. Excellent. Now we have to be careful. Your triangle may look like this. In which case, well, from a right triangle you have to subtract two smaller right triangles and a small rectangle. But you know that it holds on a right triangle and on a rectangle. Therefore, by using cutting, that's why we also did the cutting argument on the previous slides. Therefore, Pick's formula holds for any triangle now. Any triangle, that's because of the cutting. Now we are ready to prove it on any polygon. Take a polygon. As you proposed, subdivide it into triangles. Divide it into triangles. Now we know that it holds on any triangle, and by the gluing argument, it holds for any simple polygon. Yes?
Could you also do it for polygons with the cutting argument and draw a square around it?
Can you also prove it for any polygon by the cutting argument? That would be more difficult because you don't know how the polygon looks like. You can triangulate a polygon. You think of a polygon as made out of triangles, and then prove it on a triangle. On a triangle you have a nice cutting argument. On a general polygon you can, but you have to do more work to show that from some rectangle you can remove appropriate right triangles. Yes, you can run the proof on any triangle from these rectangles, so at the end you can. But we think of the triangle as cut out from a rectangle and the polygon made out of triangles. Absolutely, this proves Pick's formula. Now, look, I said at the beginning, the existence of this formula is already remarkable enough. Can you have a polygon which is stretched out, having a very large area, but avoiding points? Can you have a polygon with, let's say, a triangle with only 3 boundary points on the vertices, no interior boundary points? What can you say about its area? It will be a half, absolutely. You cannot draw such a triangle with large area. It will always be a half. Either you use Pick's formula, no interior lattice points plus half the number of boundary points, minus 1, 3 halves minus 1, 1 half. Or even if you don't remember Pick's formula, which by the way is simple enough, but you don't even have to remember, just the existence of a formula tells you that the area of this is equal to the area of any other triangle with 3 boundary points and no interior points. Even if you don't remember Pick's formula, you just draw some other convenient triangle with 3 boundary and no interior points. This one, it has area 1/2. And this will show up in the applications. Now let's take a break until 10:20 and resume at 10:20. We now discuss some applications of Pick's formula. Consider a triangle ABC with vertices on a lattice. Here we do not draw the lattice, but always remember the vertices of the triangle are on a lattice. Suppose that the triangle contains exactly one interior lattice point. Let's call it X, and no boundary lattice points besides the 3 vertices. This was the setting that we had on the first slide in the first talk. We had such examples. A triangle with no further boundary points and exactly one interior lattice point. In this case, this interior lattice point cannot be random. It cannot be just any point hanging out there in the triangle. It has to be a special point in the triangle. By looking at these examples, well, X has to be the centroid of the triangle. Anytime. There are many ways to draw a triangle with 3 boundary lattice points, no further boundary points besides the vertices, and exactly one interior point. But always the interior point, the red point, has to be the centroid, intersection point of the medians. Let's prove it. You can prove it. If you have a triangle ABC with vertices in a lattice, exactly one node inside, it must be the centroid. Look at that picture. Hint, apply Pick's formula. Try to apply Pick's formula, see what you can get out of Pick's formula. What can you say if you apply Pick's formula, yes?
There are 3 triangles.
There are these 3 triangles, absolutely. And what about the 3 triangles?
We can calculate.
Yes?
Each has the area of a half.
Absolutely, each of these, that's what you wanted to say as well, yes? Each of those 3 triangles, ABX, BCX and ACX, has the same area. It has area 1/2. Because all of these triangles, ABX, for example, contains only the 3 boundary points, the 3 vertices, and no further lattice points inside. And therefore, X divides triangle ABC, the triangle, into 3 triangles of the same area. There is only one point in a triangle which divides it into 3 triangles of equal areas. This is the centroid. Therefore, X is the centroid. Very elegant proof by using Pick's formula. And the interpretation of the centroid as the point inside that divides it into 3 triangles of equal area. Here again, we did not use the full power of Pick's formula, we only used that there is a formula that expresses the area in terms of boundary and interior lattice points. We only need to say that those 3 triangles have the same counts of boundary and interior points, hence the same area. Excellent. Now the second application is in that spirit as well. Now consider a triangle, again with vertices on a lattice, but this time it contains exactly 2 lattice points, X and Y, in its interior. There are 2 red points. It may contain further boundary points. The 3 vertices need not be the only boundary lattice points. There are plenty of such examples. For example, here, these 2 triangles, notice both of them have further boundary points, but they contain exactly 2 lattice points in their interior. Then the line joining the 2 lattice points inside is not a random line. Those 2 points are constrained in how they sit inside the triangle. Namely, the line XY either passes through a vertex, as it happens on the second example, or it is parallel to one of the sides of the triangle. It has to be like that. You're very constrained. You can play on grid paper and you can draw many triangles with 2 interior lattice points, but always that line has to be either parallel to a side or it has to pass through a vertex. Let's prove it. Now, suppose the line does not pass through a vertex. If it passes through a vertex, we're done. Suppose it doesn't pass through a vertex. Let's draw the line. Draw the line XY. Now, if it doesn't pass through a vertex, well, it intersects 2 of the sides of the triangle. Therefore, does not intersect some side of the triangle. Say it does not intersect the side AB. Now we are ready for the punchline in the proof, the key step. What can you say now? You have to prove that this line, XY, is parallel to AB. You know that it does not intersect the side AB. Prove that it's parallel to AB. Hint, apply Pick's formula. What can you get out of Pick's formula? How can you apply Pick's formula here? For which triangles can you possibly apply Pick's formula? Yes?
Right angles.
Which ones?
Right angles.
Right angles, you don't have right angled triangle. You can apply Pick's formula for anything. We proved it for any polygon, any triangle. So you're free to apply Pick's formula to whatever you want. Yes?
And how about the top and bottom shape?
The top and bottom shape.
triangle
The problem would be, if you draw the line XY, the problem would be that this point here needs not be a lattice point. Here, if you draw this line, it doesn't have to intersect at the lattice point. Now, what else can you look at and then try to apply Pick's formula? Yes?
Polygon creating different.
Which one? No. Well, let's look at triangles ABX and ABY. Look at triangles ABX, ABY. What can you say about them? Yes?
They're the same.
They have the same area. Why do they have the same area? Yes?
Well, they must have the same line.
They have the
length
same
at the
number.
bottom and the same height.
Yes, but why do they have the same area?
Boundary points.
Absolutely, they have the same number of boundary lattice points. Look at triangle ABX. What are its boundary points? Of course, AB and X. On AX, there are no further boundary points. Because inside the triangle, the only other boundary point would be Y, but the line XY does not pass through a vertex. Inside triangle ABX, there are no lattice points, because Y is not there. Otherwise, XY would intersect the side AB, but it doesn't intersect the side AB. And therefore, triangle ABX has no interior lattice points, the 3 vertices, plus it may have boundary points on the side AB. But the count is the same for triangle ABY, yes?
And then because both have the same base AB, the
Absolutely,
height is the same.
absolutely,
Same amount of
absolutely, absolutely. So by Pick's formula, ABX and ABY have the same area because they have the same count for boundary and interior points. And now you combine this observation with the conventional formula for the area of a rectangle. It's the base times the height, but it's the same base. And therefore, xx prime and yy prime, the distances from x and y to the line AB, are the same. You have two triangles with the same base and the same area, they have the same altitudes. And therefore, xx prime equals yy prime. This tells you xy is parallel to AB. We will see in all these applications, Pick's formula is particularly powerful when you combine it with conventional formulas for areas. Okay, now, is it possible to draw an equilateral triangle with vertices on a square lattice? I give you a square lattice. Can you draw an equilateral triangle with vertices on that lattice? If you prefer, I can restate the question. Draw an equilateral triangle, and then can you, after that, draw a lattice, maybe with very tiny squares. Can you draw a lattice so that the vertices are exactly lattice points? You can think either way. For now, let's think about the lattice being drawn, and now you try to fit an equilateral triangle. Can you do that? Now, you can try. Maybe this looks like an equilateral triangle, but at the end of the day, if you actually check, it's not an equilateral triangle. Now, what do you think? How many think, yes, it would be possible to draw an equilateral triangle? Raise your hand. A priori, it sounds reasonable, why not? But the others think that it's not possible to draw an equilateral triangle, and that's the answer. No. You cannot draw an equilateral triangle with vertices on a square lattice. This is a natural question. Can you draw an equilateral triangle on a square lattice? And now we're going to prove that it's not possible. Well, prove by contradiction. Suppose an equilateral triangle of side A has its vertices on a square lattice. Suppose there exists an equilateral triangle with vertices on a square lattice. We'll get a contradiction. How can we get a contradiction? With what? What can we say? We have to use our knowledge, we have to put together some stuff and then get a contradiction. Contradiction should come from somewhere. Now, how can you get a contradiction? Suppose you have an equilateral triangle on a square lattice, and let's say that the side length is equal to A. What would you look at that will give you a contradiction?
Well, the area.
The area, absolutely. Let's look at the area. Let's see what we can say about the area. Because now we have a powerful tool. We have Pick's formula. Pick's formula tells us something about the area. Let's see if we can take advantage of that. Excellent. Now, it's again particularly powerful if you combine Pick's formula with the conventional formula for the area of an equilateral triangle. Let's look at an equilateral triangle of side length A. What is the formula for the area? If you don't remember, it's very easy to deduce it. You drop an altitude, it hits the opposite side in the midpoint, what is the length of the altitude? How would you calculate it? By the Pythagorean theorem. Square root of the square of the hypotenuse minus a square over 4. You get a square root of 3 over 2. And then the area will be 1/2 times the base, which is a, times the height. Altogether you have a square root of 3 over 4. This is the conventional formula. It shows up in your geometry classes. This is the conventional formula. That's how you calculate area of an isosceles triangle, of an equilateral triangle of side length A. The conventional formula. Okay, now we have to get the contradiction. You have this equilateral triangle with vertices on a square lattice. On the one hand, the area is a square root of 3 over 4. Yes?
Well, we know that the area is the internal.
Absolutely. We also know Pick's formula. The area is the number of interior lattice points plus half the boundary points minus 1. And now we'll get the contradiction by looking at those two expressions for the area. Yes?
Yes, because I can't get square root of 3.
Absolutely, the square root of 3 is hanging out there, it's out of place. Where does the square root of 3 come from? Now, these two formulas are incompatible with each other. Absolutely, we'll spell out what you proposed, yes?
Can't you also say that it can't ever be on a lattice because the height has root 3 in it, and so it will never be on a lattice point?
Yes, but I could have a triangle and then if I drop a perpendicular, it doesn't have to be. It doesn't have to touch a lattice point. You can imagine you have an equilateral triangle and you drop a perpendicular, the foot of the perpendicular doesn't have to be a lattice point. But now, let's develop this idea. What is the square root of 3 doing out there? These two formulas, they are incompatible with each other. They cannot both be correct. And that's where the contradiction will come from. Now, let's look at what types of numbers we have on the right-hand sides. Look at Pick's formula. What kind of number do you have on the right-hand side? Don't think too much quantitatively. Think qualitatively. What kind of a number is it? Yes?
You have an integer, a whole number.
Integer or an integer divided by 2, because the worst thing you do is you divide by 2. The area is always a number like a half, 1, 1.5, 2, 2.5, 3, 3.5. That's what the area is when your triangle has vertices on a lattice. This is a consequence of Pick's formula. We don't even need the full Pick's formula, we only need the statement that the area is always either an integer or an integer 0.5. This is the type of number that an area can possibly be. Now, look at the expression from the conventional formula. Let's analyze. You have a square, you have square root of 3, and then you have a 4 in the denominator. Now, what kind of number is a square? Yes?
Positive whole number.
A square is a positive integer, absolutely. And why? Why is a square a positive integer? We have to be careful, because does a have to be a positive integer? No, a could be something like square root of 2. If you draw a joins two lattice points, maybe you'll draw a small diagonal in one of the unit squares, it could be square root of 2. It could be something like square root of 5. If it's the hypotenuse of a right triangle with the legs 1 and 2, it could be square root of 5. So a could be, it doesn't have to be an integer, but a square, what about a square, yes?
Well, the thing is that a is basically the square root of the
Absolutely, absolutely. A is the hypotenuse of a right triangle drawn on the lattice. So you have the Pythagorean theorem. A square is the sum of the squares of the two legs, r squared plus s squared. Because A is the length of a segment joining 2 points on a lattice. Once you join 2 points on a lattice, this length fits into a right triangle where the legs are integers. And therefore, even though a doesn't have to be an integer, it could be like square root of 2 or square root of 5, a square is a positive integer. Absolutely. Now you look at the two formulas. The second one, Pick's formula, on the right hand side you have an integer and an integer 0.5. The conventional formula, a square is an integer And then square root of 3, what is the square root of 3 doing out there? Let's express square root of 3 from the first formula. 4 times the area divided by a square. 4 times the area is an integer. Already 2 times the area is an integer. The area is either an integer or an integer 0.5. 2 times the area is an integer. 4 times the area is an integer. And a square is also an integer. Notice here, we are using, for this line, we have used twice that the triangle has vertices on the lattice. First, since it has vertices on the lattice, that's why a square is an integer. That's why the denominator is an integer. And since it has vertices on a lattice, Pick's formula holds. And therefore, 2 times the area and also 4 times the area is an integer. We have used the fact that the vertices are on the lattice independently for the denominator and for the numerator, twice. But now see what we got. Square root of 3 apparently is the quotient of 2 integers. Yes?
And it's an irrational number.
Absolutely, but square root of 3 is irrational. You cannot write it as the quotient of 2 integers. If you could, you wouldn't give it a name, you wouldn't call it square root of 3. It would already have a name, being the quotient of 2 integers. It doesn't. Square root of 3 is irrational. Therefore, these two formulas are incompatible, and that's why you cannot draw an equilateral triangle on a square lattice. Philosophically, what's happening is equilateral triangles, they love the number square root of 3. If you play in your geometry classes with equilateral triangles, square root of 3 appears all the time. Anytime you drop a perpendicular, anytime you compute an area, whatever you compute, square root of 3 shows up all the time. But square lattices, they repel the number square root of 3. They hate the number square root of 3. And that's why you have this incompatibility. You cannot draw an equilateral triangle on a square lattice. This is again an application of Pick's formula combined with the conventional formula for area of a triangle. Now, our last application of Pick's formula is completely mind-blowing, but it requires several preparations. First preparation, take a triangle with vertices at 0, 0, AB and CD. We're going to combine Pick's formula with the conventional formula for the area of such a triangle. You agree that if I tell you where the 3 vertices are, you should be able to tell me the area. There should be a formula that involves A, B, C, and D that tells me the area in terms of A, B, C, and D. There should be a theorem that says the area of a triangle with vertices 0, 0, A, B, C, D is something. Forget about Pick's formula for a moment. This doesn't have to sit on a lattice. Just it sits in a coordinate plane. You have coordinates for all the points. You know the coordinates of all 3 vertices. The area should be uniquely determined. Now, let's derive such a formula. Maybe you have seen it, maybe not. Yes?
Well, you would take 2 points, for instance 0, 0 and AB, and have that your base. And then the length of the base is change in x over change.
Right, so one thing is you can consider this as the base, and then you drop a perpendicular and calculate. That's one way to calculate this formula, yes?
I want to say that, or half of AB sine C, if you have the angles, but no.
You can also use a little trigonometry. Either way, one way or another, we'll do a short proof based on the idea that we already saw in proving Pick's formula. Put it in a rectangle. What are the lengths of the sides of the rectangle? Yes?
D and A.
D and A, absolutely, A and D. And then the area will be AD, which is the area of the whole rectangle, minus. Now what is the area of the right triangle on the bottom? A times B divided by 2, absolutely, subtract that. What is the area on the left?
C divided by
Absolutely, CD divided by 2. What are the lengths of the legs of this last triangle? Yes?
A minus C and D minus B.
A minus C and D minus B, absolutely. So the area would be A minus C times D minus B, subtract that as well. When you work it out, open the brackets, cancel everything, you get AD minus BC over 2. Very easy. AD minus BC over 2. Now, can I put this over there in the statement of the theorem? There is a little catch. There is a minus here. Areas do not like minuses because areas are not negative. If you imagine if A and D were small and B and C are large and all positive, this would turn out to be a negative number. So what should be the correct statement in the theorem then? I cannot just put that and insert it there because sometimes it can be negative, but how would we make it correct?
Well,
Yes?
You say given that D is larger than B and A is larger.
You can say, given that from AB when you turn to CD you go counterclockwise, I can say that. Or, if I don't want to say this, how would I make something correct out of that formula, yes?
Can you say the absolute?
Absolutely, put an absolute value, now it's correct. Always. This is the formula. Always. 1/2, you multiply the x coordinate of one of the points by the y coordinate of the other, minus the y coordinate of the first times the x coordinate of the other. Of course, your triangle could look like this. The proof is slightly different. You have to subtract from the area of a right triangle, two small right triangles and a rectangle, but the answer is the same, yes?
How do you determine which point is the first and which the second? It doesn't really matter since you put absolute value.
Once I put absolute value, then it doesn't matter. Absolutely, yes. That's why we put the absolute value, because there is no way to prefer, to make a preference, which point would be first and which would be second. Absolutely. When you put absolute value, you create that symmetry. Excellent. So this is now a conventional formula, and we'll combine that with Pick's formula in our final application. Excellent. Now, second piece of preparation. Look at the line joining the origin with the point 5,1. What is the slope of this line and what is the equation of the line? Yes?
Slope is 1/5.
Slope is 1/5 and the equation is? Yes?
Y is 1/5x.
Y is 1/5 times x, the slope is 1/5. Absolutely, this is the slope of a line. Now, I draw another line joining the origin and 3, 2. What is the slope of this line and what is the equation? Yes?
2/3 and y equals
Absolutely, the slope is 2/3 and the equation is 2/3 y equals 2/3 x. You do this all the time. Now, what is the meaning of the slope? Why is the green line below the blue line? We're always talking right of the origin, right of 0, 0. Why is the green below the blue? Yes?
Because 1/5 is less.
Absolutely, because 1/5 is less than 2/3. This is the qualitative meaning of slope. A line with a smaller slope is below the line with a larger slope. That's the meaning of slope. The slope is a quantitative measure of how steep a line is. If you ski on this green, it will be less challenging than if you ski on the blue. The blue has a larger slope. That's the meaning of slope. This will show up. This will show up. Now, third preparation. Look at the grid. Now take the origin, join with 1, 2. And keep going along this line. You're at the origin, you shoot at the direction of 1, 2, and you keep going along this line. So you prolong the line, prolong the segment. Are you going to see another lattice point?
Yes.
Yes, absolutely. And which one is the next one?
1 or 2.
2, 4. You will see 2, 4. You double it, you see 2, 4. Now if you continue along the line, what is the next lattice point you will see? 3, 6, absolutely. And then 4, 8, and then 5, 10, and so on. Once you hit the lattice point, you can keep going. You will see further lattice points, which are multiples of the first. 1, 2 is the first lattice point you see, and then 2, 4, 3, 6, 4, 8, 5, 10, and so on. You multiply it by 2, by 3, by 4, and so on. Multiply the vector. Now, this is what happens from the origin once you see a lattice point and you continue along the line. What if I connect the origin with 15, 12? Now, intentionally, I have drawn it so that from the back seats you cannot see exactly if it passes through a lattice point or maybe it's very close to a lattice point. So, give a conceptual answer just based on the numbers. 15, 12. Does this segment contain other lattice points? Yes?
Yes, because both numbers have a common factor.
They have a common factor, they have a common divisor bigger than 1. So yes, there will be further lattice points. Namely,
5, 4, and 10, 8.
absolutely 5, 4 and 10, 8. 5, 4 will be the first lattice point that you see. Now, why is that? Of course, when you look at the slope, 12 over 15, once you cancel, it becomes 4 over 5. 12 over 15 as a fraction is not written in lowest terms. You have some cancellation possible. Once you cancel, 4 over 5 is in lowest terms, and this is the first lattice point that you encounter on that line. Excellent. And then once you know 5, 4, the second will be 10, 8, 15, 12, and so on. Anytime I join the origin with the lattice point, well, there will be a lattice point closest to the origin, and then the other lattice points will be multiples of this. And the first lattice point that you encounter, the two numbers, they do not share common factors besides 1. Absolutely. If I join the origin with 20,9, you don't have to look carefully, you don't have to zoom in, you can be farther away, and if I just give you the data, 20,9, you can tell me, are there going to be any lattice points on this segment? No! And why not?
They don't share.
Absolutely, because the greatest common divisor of 20 and 9 is equal to 1. There cannot be any lattice point there. Absolutely. So this is the picture, keep that in mind. If I join the origin with something, with the lattice point, either there are no lattice points when the greatest common divisor is 1, or there will be a lattice point further closer to the origin. Now with these preparations, we turn to our last application. Here's what we do. Take capital N to be 1 and write down the fractions 0 over 1 and 1 over 1. Yes?
I just wanted to quickly ask, what if the slope is a irrational number?
What if the slope is an irrational number? That's an excellent question. If you take a slope which is irrational, what is going to happen then?
Well, I suspect that it won't pass through any lattice
It will
points.
never hit another lattice point besides the origin. So if you're at the origin and if you shoot with an irrational slope, you will never hit a lattice point. Excellent, yes, absolutely, absolutely. Now, take the two fractions, 0 over 1, 1 over 1. These are the two fractions between 0 and 1 with denominator 1. Now, when capital N is 2, we are going to write down all fractions with denominator up to 2. So I have to add 1/2. Add 1/2 between the two fractions already written down. We have 0 over 1, 1/2, and 1 over 1. Now take capital N to be 3. Now we want to list all the fractions in the interval 0, 1, bigger than or equal to 0, less than or equal to 1, with denominator up to 3. We have already written all of them with denominator up to 2. I only have to add 1/3 and 2/3. And place them where they should be, so that the fractions are in increasing order. 1/3 is between 0 and 1/2, and 2/3 is bigger than 1/2. Put them here and there. Now we have written down all fractions with denominator up to 3. Now I need fractions with denominator up to 4. Which ones do we have to add? Only 1/4 and 3/4. Because 2/4 is already in the list. 2/4 is equal to 1/2. We don't have to add 2/4. We only add a fraction in lowest terms. We always write it in lowest terms. Okay, 1/4 and 3/4. And place them 1/4 less than 1/3, 3/4 is bigger than 2/3. Now we go to n equals 5. We have to add a lot of things. Now we have to add everything with denominator up to 5. 1/5, 2/5, 3/5, 4/5. And place them where they should be. 1/5 should come before 1/4. 1/3 is less than 2/5. It's 0.4, less than 1/2. So we place them there. Now n equals 6. Which fractions do we have to add? Yes?
1/6 and 5/6.
Only 1/6 and 5 over 6. Absolutely. 2 over 6 is 1/3. It's already in the list. 3 over 6 is 1/2 in the list. 4 over 6 is 2/3. It's already in the list. You always add fractions written in lowest terms. Now add them where they should be. So 1/6 is here. 5 over 6 is there. This is the sequence that we produce. For any capital N, you can produce such a sequence. You list in increasing order all the fractions between 0 and 1 with denominator up to capital N, and all of them written in lowest terms. Such sequences are called Farey sequences. Farey was playing with those, investigating some properties. Now we're going to prove a theorem about such sequences. The theorem states that if you take two consecutive fractions in a Farey sequence, take two fractions right next to each other in the Farey sequence, let's say a over b and c over d, then something very peculiar happens about the numbers a, b, c, and d. They satisfy a certain equality. They're not just random numbers. Something happens, namely bc minus ad is equal to 1. The numerator of the larger times denominator of the smaller minus the numerator of the smaller times denominator of the larger is always equal to 1 when you take two consecutive fractions in such a sequence. Let's do an example. 3/4 and 4/5.